Alright, in this tutorial I'm going to show you the process of running a flow simulation and how to prepare the necessary files to do that. So the files that you need to run a simulation, there are 5 files, and in this particular example we're running a simulation with a model with 4 outlets, and we're going to prescribe Newman boundary condition, which is pressure boundary condition for all the outlets. And so to do that type of simulation, you need a total of 5 different files. And these are all the files that you need. Once you generate all the files, you're ready to run a simulation. And so here are the 5 files. So these 2 files are generated together by SimVascular. The 2 files, the geom.bc contains information about the geometry of your 3D model, and the restart file contains basically the initial values of pressure and flow. And so these are generated together. The numstart is just a dummy file. It doesn't really do anything, but you need it. And you can basically just copy it from the template. And then the geom.bc file contains information about the boundary conditions, and that's generated from a set of code that I will show you how to use later. And then the solver.imp is your configuration file for your simulation. And so I'm going to show you how to generate all of these files one by one. So the first, this file is easy. So I'm going to create a new folder here, and I'm going to call it sim files. So we're going to generate the files, and then we're going to put them in this folder as we do that. So the first file is the numstart file, and that's just a dummy file. It just contains the 0. So I'm just going to copy this from a template. So that's done. That one's easy. So we've got this one, and then now I'm going to show you how to generate these 2 files, and we do that using SimVascular. And so what I'm going to do is you start with your solid model. I'm going to create a folder that's called mesh, and so we're going to basically create a finite element mesh from the solid model, and then from the mesh we can generate the 2 files that we need that I just talked about. So I'm going to copy the solid model into this mesh folder, and it's a good idea to do that because when you mesh a solid model, SimVascular is going to produce a whole bunch of files, and so it's good to have a separate folder where all the files are going to be saved into. Okay, so we've got the mesh folder here with the solid model in it, and I'm going to go into this folder and then open SimVascular from here. Okay, so now I'm going to go to meshing because I want to create a mesh, and then I'm going to load our model. Click load, and I can take a look to see what it looks like. If you want to display solid, meshing solid, and then you press R, here's our model. So what we're going to do here is, in this example, we're going to prescribe pressure here, and then prescribe resistance outlet condition here. And that's also a pressure boundary condition, but we're calculating the pressure based on the resistance and the flow. So we loaded our model here, and the only parameter you need to set is the maximum edge size, and that tells the computer how finely to break the model into finite element. So it depends on what unit system your model is in. So in particular, this model is in centimeters. So this number here means, if it's 1, that means the element size, the maximum edge in the element is going to be 1 centimeter. And so usually I use something like a millimeter. And so for a model that's in centimeters, I would put 0.1. So that means I want my element size to be about a millimeter big. And then depending on how you name your model, usually you need to do this to uncheck this inflow mesh surface for the program to be able to run properly. Okay, so that's all you need to do. So I've specified my element size, and then just click run mesher, and then just click yes and yes, and then the computer will start meshing this model. Depending on the size of the mesh, sometimes it can take a while. In this case, it didn't take so long. So now it's finished meshing, and here's some information about the resulting mesh. And the number that you want to look at is the number of elements. That's usually the most important number. In this case, we got about 350,000 elements. So usually, if you have anything that's below 2 million elements, it's okay. It's not too big. I usually use something like 1 million, but it depends on the size of your model, of how finely your elements are. In different cases, there are different sizes that are appropriate. And so, if I'm happy with this, if you're not happy with this, we can go back and then change your maximum edge size to get a different size mesh. But let's just say that you're happy with this. You click OK, and then now the computer's finished meshing. Everything is stored in memory, so it's not written anywhere to disk yet. So what you need to do is you need to click on Write Output Files, and that's going to write all the mesh files into actual files that you can use later. So it's finished doing that, and then so now we've finished the meshing, and if you go back into this folder, you'll see all these files that are created. And so in this folder, the most interesting subfolder here is mesh surfaces. If you click here, you'll see it contains information about all the surfaces in your model. And so I'm going to do one trick here. The way that I've named this model is that I've named all the outlets, and then for the different segments on the wall, I named them. So there are different segments. It's not showing here, but anyway, there's different segments on the wall that are named wall underscore something. So eventually we're going to have to give an ID to different surfaces, and we will want to have to prescribe an ID to the wall. And so if I have so many wall surfaces, it becomes really cumbersome because I need to prescribe something to each one of these files. So I'm going to just show you a quick trick to make it simpler. So go back to this Synvascular, and then I'm going to go to Simulations, and then click these two buttons. And what that does is that the command here is already set to take all of the surfaces that are named wall underscore something, and then combine all of them into one file that's called wall. And the EBC and the MBC are just the element and the node. So the file here contains information about the elements, file here contains information about the nodes. Okay, so I've done that. We don't need Synvascular anymore. I'm going to close it. So what that has done is it has combined all of these wall surface information into a combined wall EBC and MBC right here outside of this folder here, and we're going to use this later. Okay, so let's review what we're trying to do. So we've now meshed the solid model, and what we're trying to do now is we're trying to get these two files, restart and GeombC. So the way that we're going to do that is from the mesh folder. When you mesh it and you save it, you're going to get a file that's called something cvpre. And so we're going to modify this file. And the way that we modify this is that you open it and then you look at everything that's after adjacency. We're going to get rid of it. Okay, so before this line is what you want. And I'm gonna open the template CV pre and copy stuff from there. So I want to copy everything that's after. Okay. So we won't have to modify this because it's already what I want, but I'll explain what the different parts are. So first of all, you need, if you're running a rigid simulation, you need to prescribe no slip boundary condition to the vessel wall. And so remember, we've combined all the wall into one file that's called wall MBC. It's right here. And so we're going to have wall MBC right here, prescribed no slip. But if you have multiple walls that are not combined in the same file, then you need to add multiple lines to prescribe no slip condition to all of them. And then here, anything that's has a pound sign in front of it is commented out, so we're not going to worry about it. Remember, in this example, we're trying to prescribe pressure boundary condition to all the outlets, and we have 4 outlets. And so that's why we need these 4 lines here. It's prescribing a pressure condition to the 4 outlets. And the way that you need to modify these is that if you would look into your mesh surfaces folder and you would prescribe the right names to these lines. And so you don't need to change the EBC or whatever, just change this part so that they're matching the outlet surfaces that you want to prescribe the pressure boundary condition. If you don't know which surface is what, there's one way you can find out, and I'm going to show you how to do that. So I'm going to go into this folder, and I'm going to open ParaView. And then I'm going to load all of these, and I'm going to load all of these. Basically, I'm loading everything, but I'm loading them separately because, well, it's too hard to explain here, but you can just load all the files that you have, and then you'll be able to get something like this. And so the way that I find out which surface is what is I basically just uncheck. Okay, so this IVC is this surface, and then LPA, you can just click toggle them and you can see which surface is which. And then I have the different walls, so these are all walls. Alright, so that's how you can find out which surface is what in the actual location if you don't already know. But when you're making a model, you supposedly have named these surfaces so that you know which is which. So that's how you find out the surfaces. Okay, so you've now prescribed pressure boundary condition to all the 4 outlets. And then lastly, in order to run the simulation, you're gonna be prescribing some boundary condition, details of the boundary condition to the outlets. And so in order for the simulation to know what's going on, you need to give it an ID that you can refer to later, and that's what this section is doing. And so don't change this line, we just always have this, so all the surfaces together is assigned ID 1. And then for the rest of the outlets, you put the right names here, and then you assign a number behind it, and that's the ID that the outlet will be referred to. And so this you can just do it arbitrarily, but you need to remember what you assigned them so you can refer back later. And then these 2 lines just writes out the 2 files that we want. So once you finish editing this file, you save it and you close it. And then now I'm still in this folder, and what I'm going to do is I'm going to type pre-solver and then the name of the CV pre file, and then click enter. and now it's going through the whole thing to generate the two files that we want. Okay, so it's generated this file and this file. So that's, and I'm gonna drag it into our simulation folder. Okay, so now we've got 3 of these files. So going back to, we've got this one, we've got this one, we've got this one. I'm going to show you how to get this one. And so again, we have a template one here you can use. I'm going to start. I'm going to start with a template, and then I'll show you how to modify it according to what you need. So I copy it here, open it. Okay, so the structure of the solver file is that here you have this line that you define how many time steps you want to run of the simulation, and here's the time step size. So right now it's set to 1 millisecond time steps, and then this is saying that I want to run 6,000 time steps, which means I'm running 6 seconds of real time. And usually I usually use around 1 millisecond, but if you're running into stability problems or if you want better resolution, then you can change this number. But then you need to change this one depending on how much real time that you actually want to run. And then here you're defining the viscosity and the density of the fluid that you're running, and this has to be consistent with the unit in your solid model. And so we usually use, so there are three units that you need to specify. One is distance, one is mass, and then one is time. With these 3 units, you can basically specify everything in the whole universe. And so usually for mass we use grams, and then for time we use second. But for distance, depending on what your model, the unit of your model, it could either usually be centimeters or millimeters. And so because our model is in centimeters, then the units of viscosity and the density have to be in centimeters. And you can do your own calculation and just to check to see if the values are in the correct unit system. You need to look up the unit for viscosity and for density, and then break it down into distance, mass, and time, and see what the right number is. But I'm just going to change it right here because I know in centimeters my viscosity is 0.04 and my density is 1.06. So they just need to be consistent with whatever unit system that you're using. And then this line right here tells you how often you want to save the results. And so this is saying that I'm saving the result every 20 time steps. And so that means, if I'm running 1 millisecond time steps, that means I would have 50 sets of results per second. And then don't worry about this one. And these 2 are commented out. And again, anything that starts with a pound sign is commented out. Don't worry about these. Number of coupled surfaces. We have 4 surfaces. You need to set 4. And don't worry about these 2. Number of Newman surfaces, because we're using pressure boundary condition, so those are called Newman surfaces. And so we've got 4 of those. And right here, the list of surfaces, now you're basically telling the simulation which surfaces are supposed to be the Newman surfaces. And that's where the ID that you set before comes in. So let's take a look at this file that we had before, the CV pre file. So here we've got ID. These are the ID of each one of those surfaces. And so the order which I put the surfaces is important for later when we're assigning the boundary conditions of what's happening at each boundary. We're going to have to take care of the order. So, but right now I'm just going to put everything in the same order. So these are the 4 surface IDs that we want to assign the Newman boundary condition. And so we just need to know that 2 is referring to the IVC, 3 is referring to the SVC, and so on. Okay. And then this, we'll just leave it as it is. Don't worry about this. And I think that's it. There's nothing else we have to change. So this file is ready. Save it, and we can close it. Okay. So now we've got 4 of the 5 files that we need. So I'm going to show you how we get the very last one. And this is the last one is this GenBC file, and it tells the simulation what happens at the boundary. So this is the boundary condition files. And this is going to be the most complicated one in our case to generate. So the way that we get this file is that we use a program to generate it, and the program is in the folder right here, the BC folder. So you go in here, and there's really one file here you need to edit to get what you want, and that's the user.f file here. So I'm going to open it, and I'll show you. I mean, you don't need to understand everything, but I'll show you the parts where you need to edit. And so I'm going to start right here. And so you need to set the right number of surfaces. So if we have 4 Newman surfaces, then we need to set this number to 4. If you have a Dirichlet surface, then you would, because we don't have any flow surfaces where we're prescribing flow, and so we have 0 here. And then for simplicity's sake, in this case, we're not solving any differential equations, so we just need to have the same number of unknowns to describe each surface. If you have a more complicated downstream circuit, you might need more unknowns to calculate those, but at a minimum you need to have the same number as your surfaces. Okay, so these are 2 things you need to look at and to correctly set. And then right here you need to set the initial values for your boundary. So since we're prescribing a pressure boundary condition, then we're setting values of the pressure. And so this just tells the computer, at time step 0, when it hasn't solved anything yet, it needs some number to begin with. So this is just a guess that you're entering, and then so that you're able to actually kick off the simulation. And so in this file, the 4 boundaries are known as the 4 x's. Let's see how I can explain this. So we've set here that there are 4 unknowns, and so we would call them, let's just say we call them x1, x2, x3, and x4. So as far as this file is concerned, it only knows about these 4 things. It just knows that it has 4 unknowns. That's all. And it's trying to figure out what the values are for these 4 unknowns. And so I'll come back to this later. I'm going to talk about the next thing you need to look at is this line right here. So as I was talking about, this program only knows that it has 4 unknowns. It doesn't know anything, like it doesn't know what these unknowns are. It doesn't know, it doesn't know anything else. It just knows it has 4 x's. And so what this line does is that it connects the unknowns here to the actual surface that you're trying to prescribe. And the way that happens is that, remember in our solver file, we have, actually I'm going to open this too. Okay, so in our solver file, we prescribed the surface IDs right here. And the way that this works is that the number that you put here tells this program which surface each of the x's is pointing to. So you can, there's some explanation here. You can, if you forget, then you can read it and try to understand what's going on. But basically, the order which you put these numbers is important. So the first number here corresponds to first number here. The first number here corresponds to first number here. And so the way that it's set up right now, what this means is that x1 corresponds to surface ID 2, and x2 corresponds to surface ID 3, and so on. Now, how do you know which surface this is? Well, then you need to go back to your CVP file and look at, well, my surface 2 is IVC, my surface 3 is SVC. So there's a lot of indexes in different files. You need to make sure that everything's consistent and you're actually prescribing the right boundary condition to the right outlet. So anyway, that's what this is doing. So once you've done this, then each of the x's is assigned to the right outlet surface. And then in this case, we have x. So again, going back to the initial condition that you need to prescribe, these are the initial values for x1, x2, x3, x4. If you have a different number, if you only have 3 outlets, or if you have 5, then you need to add additional ones. But it's got 4 right now. And so we're assigning the initial values for the different boundaries. So in this case, we have x1 and x2 pointing to the inlets, so the IVC and the SVC, and then we have the outlets, which I'm just prescribing 0 pressure. Okay, so that's that. And then, so in this case, in this example, what we want to do is we're trying to prescribe just a constant pressure at the inlets and then resistance at the outlets. And so we know that x1, x2 are our inlets, as we've just talked about. And so I'm going to prescribe some pressure here. And remember, everything is in CGS. And so I'm going to prescribe the pressure that I want is 10 millimeter mercuries. And so I'm going to convert that to CGS unit, which is this number right here. And there's one thing about Fortran is that anytime you enter a number, you need to type d something. Well, this d is the exponent. It's like 10 to the power of something. So if I just want the number by itself, then I type d0. If you don't do this, it's not going to compile. Fortran is annoying like that. I hate it, but that's the way it is. Okay, so what I've done here is I've prescribed 10 millimeters of mercury pressure at my surface x1 and x2, which are my inlets. And then don't worry about these. We're not solving any equations here. And then right here is where we prescribe the resistance boundary condition for the outlets. And so what we've done here is that the way that the resistance boundary condition works is we're assuming that we start from 0 pressure, and then we have some flow into the resistance, which creates some pressure at our actual outlet. And that's described as an offset from the 0 that we have. I know I'm not explaining this very well, but for the purpose of this example, just take it as it is. And what we're going to do is we're going to prescribe the resistance boundary condition by setting the correct pressure using an offset function. And so the outlet are the x3 and x4. And so we want to offset x3 and x4 right here with the right pressure. The way that you calculate the pressure is flow times resistance. And so the flow, and so that's what this is saying. This is the flow. This is our resistance that we've set. So the flow that you want to use, let me try to explain this. The flow comes from the 3D domain. So this whole program calculates the 0D domain stuff. And then it gives pressure, it calculates the pressure and then gives it to the 3D domain. And then the 3D domain takes the pressure, calculates the flow, and then passes the flow back into this program so that this program can now use the flow to calculate the pressure for the next time step. And so basically this program is receiving pressure information. This program is receiving flow information from the 3D domain. And because it has 4 interfaces, there are 4 outlets, so 4 interfaces with the 3D domain, there's flow Q1 to Q4. And the way that you know which Q corresponds to which surface is you look at the order which you've assigned the x's right here. And so this x corresponds to Q1, this corresponds to Q2, this corresponds to Q3. And so right now everything's nice, but if I had switched this order and put 2 here and 1 here, then x2 would correspond to Q1 and x1 would correspond to Q2. And so you just need to, again, this is one of those things, the indexes you have to keep track of. You just need to make sure that you're using the right flow and the right x, which correspond to the right outlet. All right, so anyway, so we've identified the correct Q for this surface, and then here's the resistance that you can specify. And depending on the flow that you want, this is a value that you assign. So we do this for both of the outlets, and that's it. You've finished editing this file. Now you can save it and close it. Now here's the last step. So I've gone in here, I've edited this file, I've saved the file. Now what you do is you go into this folder and then you type make. And that's it. The program has generated this file called genbc, which you can now use for your simulation. And now remember, it's important that you need to do this step to type make on the computer which you're going to be running the simulation from. So if you're going to run the simulation from Vivian, you need to copy this whole folder to Vivian and then type make there so that you would compile the information using Vivian. And if you want to run on your own computer, then you would need to do this step on your computer so that this file that's generated is suitable for the computer that you're going to be running simulation on. Okay, so we've got our sim files, and we've got our last file that we need, and that completes the process of generating all the files to run the simulation. So now you basically have everything that you need to run a flow simulation.